Okay, let's start. So, we'll be looking into different types of fields out there, and also we'll try to start motor effect. Motor effect is like the next topic. So, last class I just started this. We didn't actually complete this or go any further, which was what's the pattern of your magnetic field around a current carrying conductor? And we found that the magnetic field pattern around a conductor is like circular or it's concentric. That's the right term. And you'll find that ekhane jeta hoy is that as you start from here and you go further out, the lines are actually spreading out, which indicates that there's an increase in strength here, right? And there used to be a formula for this before. We formula from the night down the magnetic flux density for a flat, like a single wire, is mu I divided by 2 pi r. এখন এখানে I-টা কি? I is the current in the wire. So that means the strength of your magnetic field here depends on the current. And R here is the distance from the wire. So it means your magnetic field is what to the distance, inversely proportional. So the further you go, the weaker it becomes. এখন তোমাদের A2 তে they want you to learn 3 different fields. The 3 different fields আজকে আমরা দেখবো. So first হচ্ছে conductor. So you've seen that already. এটা লাগবে না, এটা আমি আবার নতুন করে দেখাচ্ছি তোমাদেরকে. So conductor এর কি কোনো প্রবলেম আছে তোমাদের? This one. So how do you find this? I'll give you a summarized note on this, but before that, just can you tell me the rule that helps you find out the magnetic field pattern or direction around a current conducting wire? Right hand? Right. So there are 2 rules out there which are a little overlapping with each other. একটা হচ্ছে right hand grip rule and the other one is the right hand rule. Do you know what the difference is between the right hand grip rule and the right hand rule? Yeah. Where do you apply the right hand grip rule and where do you apply the right hand rule? The right hand rule is for the solenoid. Right, exactly. So this one has multiple names. It's called the right hand grip rule, or there's another name for it, the official name jeta, or the, do you know the other name? No, it is different. It's no, a topic Fleming Fleming came later on. So Fleming's left hand rule, Fleming's right hand rule, those are not here. Anyways, this is also called the corkscrew rule. Corkscrew rule. So this is the actual name, but they made a modification and they call it the right hand grip rule. Okay, so what does this rule allow you to find? You have to know what it does. So it allows you to find the direction of magnetic field around a current carrying wire. That's it. So direction of magnetic field around a current carrying wire or current carrying conductor. Doesn't need to be a wire, anything of similar sorts. Okay, so yeah, this is the wire, current carrying wire. This is the first one out there. আজকে যেটা করব number 2 হচ্ছে O level se over ছিল না, but it was there, we didn't focus on it. It's called a flat circular coil. What is the magnetic field pattern going to look like for a flat circular coil? এটা হচ্ছে current carrying conductor. Right, so how is the magnetic field pattern going to look like for a flat circular coil? So what's a flat circular coil? It's basically you take a wire and you make a circle with that wire. So it's like that. It's flat circular coil like that. So how does the magnetic field pattern look like for this? That's the question that you have in your syllabus. For ever, I have never seen any question based on this. Until I think very recently, they asked you to just draw this for 2 marks. You draw the magnetic field pattern around the circular, flat circular coil. Now, this was there in your O levels, and this was actually something that made you understand what a electromagnet was. So let's assume, Jay, you don't know what this is, right? কেমনে এটা বের করতে হয়? How do you find the magnetic field around a flat circular coil? So the way you do this is you first imagine not a flat circular coil, but a rectangular coil. So let me show you what I mean by that. So imagine there's a coil like this, not really a coil, a structure. It looks like that. And this structure, the structure looks like this. I think you'll remember now. So the structure looked like this, and we passed what through the structure? Current. Okay, so do you see it looks like a doorway? Like a doorway moton dekhte. Right, there you go. বুঝা যাচ্ছে? It's like a door, right? Acha. Now what's going to happen is current is going to flow through this. So current will go this way, এদিকে যাবে, and the current will go that way, and current will go this way. So you need to find out the magnetic field pattern around this flat circular loop, both of our circular and a rectangular loop. So how do you find this? So the first thing that you do is you find the magnetic field pattern for this wire only. So can you tell me how does the magnetic field pattern look like? Khali wire, just this wire. It's circles, right? So কিরকম দেখতে হবে? Like that. Sorry. It look like this. Do you agree? So the magnetic field pattern for this particular part of the wire is going to look like a series of circles here. It has the 3 dimension আছে, so আশা করি তোমরা বুঝতে পারো কি হচ্ছে এখানে, but this is how the pattern looks like here. So pattern টা হচ্ছে you have these circles, concentric circles, and I'll just draw a few of them, not all of them. So এরকম দেখতে. Is it okay with everyone so far? Acha, এখানে হচ্ছে the thing is this is just at one place. Do you think that the field is just here, or do you think the field is everywhere? Everywhere, right? We just have drawn this one location for understanding purpose, and a part হচ্ছে behind the wire. So now question for you, can you tell me what is the direction of the magnetic field on this red circle? So how do you find this? The right hand grip rule, you point your thumb upwards, right? So এদিকে হচ্ছে thumb upwards করবা, and then see how the fingers wrap around this thing, right? So if that's the case, can you tell me A side A, which way should the arrows be? Anti-clockwise, correct, right? So it's gonna point like that, and it can also like this. Do you guys agree? Okay. Now similar pattern will also form up here, upor ei jagataয়, and এখানে হচ্ছে you have this thing like this. So can you tell me how does the magnetic field pattern look like up there? এভাবে you draw করি. Again, the right hand grip rule. Can you tell me on the front side which way the arrows point? Yeah, very good. Downwards. Okay. So it's gonna point downwards here, down like that. So I think you understand the basic idea behind this. So if I do that here, you'll find this is going to be like that, and that is going to be like that. And if I take this one here, and if I place it down there, you'll find that inwards, downwards on that side, and what on the front side? Upwards. Are you with me so far? Acha. So what did I do is I took a flat rectangular coil and I found the magnetic field around it, right? Now, if you look at the structure once again, you'll find that there's something happening here, which is the net magnetic field in this structure is always entering. I'll show you what I mean by that. Think of this as a doorway. This thing is a doorway, right? Do you see that all the field lines are going into the doorway? If you look at the field here, it's this place. It's entering here, it's entering there, it's entering there, it's entering there, right? So if you take the net field here of all the field lines combined, right, what do we find? We find that once you combine all the field lines here, it forms a combined magnetic field that looks like this, where all the field lines that you see, they're entering from this side. They're entering from like this, like this, like this, if you add all of them up, because they're vector, right? And from the other side, what are the field lines doing? Yeah, exiting, right? So from the other side here, you'll find that the field lines are leaving from the other side, like that. And if you do this, and you draw the arrows and everything, you'll find that the arrows on this side all look like that because it's entering, and the arrows on the other side, they look like that, which means they're what? Leaving. And this mimics something. What does it mimic? Yeah, so if I block this out, and let's say I told you what's not, like, I didn't tell you what's inside, and I just told you এরকম একটা structure exists for it, where you have field lines entering from this side and you have field lines leaving from that side, and I asked you what might be inside, right? It looks exactly like a bar magnet. In a bar magnet, you have one side where all the field lines are leaving, and on the other side you have all the field lines entering, and that just looks like a bar magnet. And what we have created here is a structure that resembles or mimics a magnet, but we don't have a magnet here. We don't have any ferrous material. In fact, this thing is not even made up of iron. So, like, somehow we have manipulated the current to produce a magnetic field here that looks exactly like a magnet, and it behaves like a magnet as well, right? And that's why this is called a what magnet? Electromagnet. Okay, so an electromagnet is a device that shows magnetism because of the passage of what through it? Current, right? Also, furthermore, you have more advantages than a normal magnet. Why? Can I increase the strength of this magnet? Yes, I can increase the strength by increasing the current. I can increase the strength by increasing the number of turns or number of coils. Yeah, number of turns in the coil. Coil is the structure and number. And then if you say increase the number of coil, that's not actually the right thing. You're increasing the number of what in the coil, turns in the coil. And the other thing you can do is you can place something inside that will like strengthen and concentrate your field lines. What is that? Yeah, you can place an iron core inside, and once you place an iron core, what happens is all the stray field lines so all these random lines that you see there, they'll move into the iron core, because iron has this ability to attract magnetic field. And then all these field lines, number of field lines same thing you can do, but the number of field lines that are same is in what area now? Smaller area. And we learned the other day that is what B represents, magnetic field strength, and magnetic field strength increases. Okay, so yeah, this is the origin of your electromagnet. But we haven't answered our original question though. What is the magnetic field pattern going to look like for a flat circular coil? So ওটা কিরকম দেখতে হবে? So it comes from there. আমি একটু draw করি, তোমরা আমাকে বলো যে কি হবে. Just a second. Right, so flat circular coil here. Which part is the back side of the coil? So that part is the back side of the coil, dotted line, and this side is the front side of the coil, and there's current passing through the coil in this direction. Okay, if I current that's it, like that, and like that. Can you tell me how does the magnetic field look like here? So the magnetic field here will enter all from one side and leave from one side, right? So এটা কেমনে বের করতে পারি? So the way you do this is তোমাদের বইতে এটা mention করে নাই, but most books I think mention করে. Picture it differently. Picture this thing not like a flat circular coil on a table, but a flat circular coil passing into the table, and you'll find the answer becomes super easy. Maneki, this is the diagram I'm looking for. So there's a coil like this, and the coil has been cut through the table. I'm putting a draw it, I don't like a better visualization of it. So you're basically making what in the table? Holes. And ওই holes গুলোর ভিতর দিয়ে তারগুলোকে নিয়ে যাওয়া হয়েছে. And the wire goes through the table, beneath it, and comes back from the other side. Can you picture it now? Acha. If I draw this thing and I tell you the current is going this way, and the current goes that way, and the current comes down here and back down here, right? And you look at this particular place, like here, and you imagine that there are magnetic field lines like that around this, right? So here. Can you tell me what's the direction of the magnetic field lines around this wire? That will solve all your problem right now. Just tell me এইটার arrow গুলো কোন দিকে হবে? Yeah, very good. Anti-clockwise, right? So anti-clockwise মানে হচ্ছে you'll find that the arrows are pointing like this. Do you agree? Similarly, if I drew that same thing on the other side, like here, you'd find that the arrows are going to be which way? Clockwise, right? Which would mean that the arrows are like that. And the thing that you should look out for is that these arrows are pointing in that way, these arrows are pointing in that way, which means the total magnetic field here actually looks something like this. So what's the net magnetic field going to look like? So this view is not the right view. I'll show you the top view. But the net magnetic field looks like this, where field lines are getting curved around like that. And as they start to approach the center part of your coil, they start to what? Straighten. Straight হয়ে যাচ্ছে, and they become like this. And the more you go towards the center, the more straight they become. And right through the center, they'll have like almost a straight line. Okay, so এই জিনিসটা এই সাইডে হচ্ছে replicate হবে. So it's supposed to look something like this. It's not the best view. The best view is the top view. But the point I'm trying to make here is that all these lines that you see here, they actually look like what? Straight lines like this, right? And if I put the arrows here, it's a aerocomb. Do you see all the arrows are entering from one side and leaving from the other side? মানে যে এখান থেকে সবগুলো এন্টার করতেছে আর ওদিক থেকে লিভ করতেছে, দ্যাট ইজ হাউ দ্য প্যাটার্ন সাপোজ টু বি। সো এক্সামে তোমাদের ড্র করতে দিলে এইভাবে ড্র করতে হবে, বাট অবভিয়াসলি ওরা এই ভিউ দেয় না। ওরা কোন ভিউ দিবে? আইদার দে উইল গিভ ইউ দিস ভিউ, যেটার মধ্যে লাইনস গুলো এরকম দেখতে হবে, এই যে এরকম, লাইক দ্যাট। Do you understand how am I drawing this right now? So this is basically which version? এটা হচ্ছে এই যে এই ভার্সনটা, মানে you know, if you see it from that side, I'll show you a better picture, don't worry. But the point is, this is what you need to learn. Now, this was there in your O levels. I mean, to O level like a note that I mean, O level note attached to it because it's more detail, I think. On the A level search, we have, you know, more important things to do. So I'll just quickly go through the things that you need to recall from your O levels. Okay, basically the entire magnetism chapter. Right. So here. Do you see this? This is basically the flat circular coil, but this is the flat circular coil from which side? The top view. And if you see these small dotted things placed around them, right? What do you call them? Iron filings, right? And as you place the iron filings here, they form this pattern, and a pattern. And do you see in the center, the lines are almost straight. And on the side, do you see they're spinning around like that? Also, you'll find the concentration is more towards the around the wire and then around the center for multiple reasons. Number one, the strength is always stronger around the wire. But at the center, you have field lines from here and field lines from there, both entering that place. So they're vectors. What do they do to each other? They add up because they're in the same direction, right? So eventually, this is a pattern that you have to draw. Exam যদি দেয়, top view দিবে, dot and cross দিয়ে দিবে এখানে, তোমাদেরকে যেটা draw করতে হবে is something like this. Between the center and the coil, মানে এই জায়গাতে এগুলা, oh yes, because you're going further away from the wires, so it's getting weaker, and you're going further away weaker. But by the time you reach the center, this one and this one both have like a good enough value, so they add up and they make it strong. Okay, so yeah, this is the 3D version of it. Okay. Right, so this is the magnetic field around the flat circular coil. That's another version of this, right? It was the one I was trying to draw. The center always have a strong field. Yes, the center will always have a strong field in this scenario. But if you have two random wires, parallel wires carrying current, right? Center মাঝে মাঝে strong হয়, মাঝে মাঝে weak হয়. And that's why there's this thing that when current passes through two parallel wires in the same direction, right, the wires move towards each other. And if they're in opposite direction, the current, the wires move away from each other. There's the magnetic fields like add up and don't add up. We have that later on. It's part of motor effect. Okay. So yeah, these are the fields that you need to know. Now that's one coil. You see this thing? This is one coil here, right? The magnetic field of one coil. Now, if you take many coils together and stack them up, কি হবে? Do you see what happens to the amount of strength you get from each of them? It amplifies. It's actually a perfect multiplicative factor. মানে কি? One wire gives you 1, 2 will give you 2, 3 will give you 3. So if I want to increase my magnetic field strength 1,000 times, right? What do I do to a number of turns? 1,000 times, right? Now, if I want to increase the strength of my electromagnet, right? What should I do? Electromagnetic strength bound, there are many ways, but can you tell me the top 3 ways of increasing the strength of an electromagnet? That's an electromagnet, okay? So an actual solenoid. So it's just a coil there. It looks like a spring. So as you pass current through it, the magnetic field that's generated around this thing will mimic the magnetic field of what? A magnet. And that's what's called an electromagnet. So to increase the strength, there are 3 things you can do. একটা হচ্ছে place what inside? Iron core, which is missing. And or you can increase the number of what here? Turns in the coil, or you can pass more current. Can you tell me which one is practically the most effective way? coil, turns in the coil. Why? Because it's a multiplicative thing. আমার 10টা দরকার, I want to increase my strength 10 times, right? I'll just put 10 times more coil. But the thing is, it's not practically feasible though. কেন? আমার ফ্যানের স্পিড বাড়াতে চাচ্ছি, and I want the force increase and everything. I can't practically go there and change the number of turns out there. So তখন we rely on what to change the current. That's it. But current কিন্তু effect অত বেশি না. Current এর speed 1, 2, 3, 4, 5. It's basically you can change it 5 times maximum, because তার বেশি গেলে যেটা হবে, the current is too much and the thing will start to what? Overheat. Okay, and then it will lose its efficiency. So manufacturing point of view, the first thing that you try to do is increase the number of turns. Practical user point of view, where you want to manipulate and change the value on the go, we change the what? Current. And the thing that is supposed to be there by default to have a strong magnet anyways, an iron core. Okay, why not a steel core? Right, once again, O levels. Steel is a hard magnetic material, which means it's very difficult to magnetize, but it is very difficult to demagnetize, right? Electromagnet, one of its selling feature is what? You can turn it off. So if the permanent magnet ho jay, tale to off hobe na. Tumi current off kore dile, but what will it still remain? A magnet. We don't want that. Okay, so yeah, that's how these things work. Now, one last thing before we move on is this one. How do you find which side is the north pole and which side is the south pole of an electromagnet? It is called the right-hand rule. Okay, so right-hand rule ta ki korte hai? By the way, officially this is not like allowed. It's only unofficially we talk about it. To find the north and south, you take your right hand, but your fingers will now point in the direction of what? Current. Where? On the front side of the solenoid. So on the front side of the solenoid, where is the current pointing? Upwards. So right hand niye hocche upor dike point koro. Once you point your right hand upwards, jedike tomar thumb thake, that's your north pole. So basically, you try to hold this solenoid. Like, if I try to grip the solenoid with the wire, you see where my thumb points? That is going to be my what pole? North pole. So you can not take the cast, right? However, do you remember what was the official way of doing this? Yes. Yeah, so the official way, not very intuitive, but this is it. That when you look from a particular side and you see the direction of current to be clockwise, it's a south pole. So the official rule হচ্ছে তোমাকে আমি একটা coil দিলাম আর তোমাকে বের করতে হবে which side is the north pole or south pole. কি করবা? যে কোনো একটা সাইড থেকে দেখবা. You look from a side and you see the current in that side. If the current in that side is clockwise, it's a south pole, right? And if the current happens to be anti-clockwise, what would that be? North pole. That's the official way of saying it. Okay, so do you see that the current is going like that? Isn't that clockwise? So that's going to be south. The way they want to like they market this by saying that south এর মাথায় arrow দিলে হচ্ছে clockwise একটা direction form করে, north এর tail এ একটা arrow দিলে anti-clockwise form করে, for you to remember. I don't know if it's memorable, but the point I'm trying to make is that south jodi hoy, how do you know clockwise and anti-clockwise? Just put arrows like that. And what kind of direction is this showing right now? Clockwise. So when it's clockwise, it's a south pole. And if it's a north pole, erokom kore anti-clockwise. Okay. Right. So these are the things that we have. Thickness of the wire. So thickness of the wire affects strength of a magnet indirectly. Why? If you increase the thickness of the wire, the resistance decreases. And because the resistance decreases, more current can pass through. But just the thickness doesn't do anything. Okay, so let's just, before I give you the notes and everything, so the first one is your current around the conductor. Eta hocche right hand grip rule use kori amra. Thumb ta ki represent kore? Current. And what do the fingers represent here? The direction of magnetic field. What are the factors that affect the strength here? The current, the number of turns or loops in the coil, right? So that's how it is. The further you go, what happens to the strength? Decreases. Okay. Right, and this is the flat circular coil. So flat circular coil, this is the diagram I was trying to draw, right? So ekhane ki hobe that eta kintu right hand deo ber korte paro. Like, you point your fingers this way. Try koro right handed. Right-handed, point your fingers in the front side, right? This way. Which way is your thumb pointed? Upwards, and the upwards must be a what pole? Okay, so that's the. So I'm gonna get a solenoid. Solenoid is basically a what version of this? Side version with more of these stacked next to each other, right? So there, and this makes it a what magnet? Very strong magnet, right? কারণ প্রত্যেকটার ফিল কি করে একটা করে অ্যাড হতে থাকে। So this is basically where your solenoid comes from. But তোমাদের এক্সামে হচ্ছে just one single flat coil আঁকতে বলে, that's how this is supposed to look like. No confusion? Yeah, so take your right hand and the finger will be the direction of your current on the front side. On the front side, yes. So which is your thumb pointed. Yeah. Okay. Always remember, if you want to use a right hand rule, the fingers should point in the of the current on the front side, not the back side. And yes, solenoid হচ্ছে এটা, so solenoid এর মাঝখানে হচ্ছে you can place a core and make it stronger, and yeah, that's essentially it. Okay, so these are for your A levels. Like I've given you whatever I've just mentioned so far. I'll also add the O level stuff, just in case you want to learn from scratch. Okay, so yeah, these are the types and patterns of our magnetic field. So on the syllabus of keyboard say you need to know current carrying wire. Are you okay with this? Current carrying wire? Acha, you're supposed to know for a flat circular coil and a solenoid, the one that we just viewed. Okay. Also understand the magnetic field in due to the current, a solenoid can be increased by a ferrous core. Why is it like that? Why is the presence of a ferrous core going to make your electromagnet stronger? Right. Yes, very good. Okay, so iron mode, there are a lot of dipoles randomly lying around, right? Once the magnetic field of the coil passes through the iron, right, those random dipoles get what as well? Aligned. And now they add to your already existing magnetic field, so it becomes stronger. Okay. And explain the origin of forces between current and so that's what we're going to see right now. It's the motor effect. Okay, but yep. So that is what you have to know for your A level search diagrams below. Demonstration so there are a few of them. We have gone through these before. Yeah, look at this. Basically, this is your right hand grip rule. So I can change the orientation of this thing. So if I take this red color thing, do you see the thing I'm moving around? What is it? Plotting compass, and do you see that it's going like that? So current jodi hocche upor dige hoy like that, your magnetic field is going to be what? Anti-clockwise, right? So do you see it's anti-clockwise? And you'll find the closer I come, with B arrow ta boro hoye geche, and the further I go, B arrow ta choto hoye jacche, because that B represents what? Magnetic field strength, right? So yeah, that's basically the idea, and it's called the right hand grip rule. So that's one thing that we saw. Our okay. Sorry. Yeah, but the one for the solenoid is not. That one is the north and the south, clockwise, anti-clockwise. And just a few more things about magnetic field before we start the A level part. So magnetic field happens to be three-dimensional. We always draw it 2D, but it's actually 3D. So when you do the different point of view, you'll find that it's actually a little different than what we picture. That does play a role in reality, but তোমাদের সুবিধা হচ্ছে যে you don't look this view. You see from which side? The front. And front থেকে দেখলে এরকম দেখতে মনে হয়. The lines going from where to where, north to south, right? Also, you'll find that this is exactly a mimic of the Earth. So Earth, our magnet যদি shift করতে থাকি, they have the exact same field pattern. But surprisingly, there's no magnet inside the Earth. So there was a belief that there is a magnet inside the Earth. There's no magnet inside the Earth. In fact, there's no magnetic material inside the Earth. There's an iron core, but that's not actually creating the magnetism. So the origin of magnetism inside the Earth is a little mysterious. Currently, what we understand is that the liquid material, they're flowing around, they're charged. And because that liquid core is charged, flow of charge produces what around it? magnetic field. It just happens to be this very random coincidence that they flow exactly like this, creating a what at the top, north, and what at the bottom, south. That is wrong. So they create a south at the top and a north at the bottom. Do you know that? No? Wait, how come? We talked about this, right? So the Earth's poles are actually inverted than what we know. So North Pole A, Earth's cone pole, magnetic south, right? Otherwise, why is the North Pole of your compass pointing to the north? Shouldn't they recall? North Pole of a compass, right? If north they point for it. No, we are not upside down. The magnetic field is upside down. So if your North Pole points towards the north, how much of the north must be a what pole? South Pole. There was a mistake. Paragichunai, 1,000 years back, they started doing this. They saw that the compass points that way. They started calling it north. Eventually, they realized one day somebody had this, moment of enlightenment. Say, wait, north to the north point for it. So that's not a north. That must be a south pole. And eventually, it turns out there's actually a south pole there. Okay, doesn't change anything for us. But there are navigate for a pilots, for example. They use the true magnetic north, which is at the south pole. What they were chalo navigation for it. Yeah, I think so. Acha, one more thing. Igla, just just to clarify if you have doubts. No. And Jupiter. No, Jupiter again, magnet. So yeah, this is the magnetic field around a bar magnet. I bring another magnet here. Do you see how the lines interact? Right. So that's how magnetic field lines combine. You'll find one thing happen here, which is the lines will never what each other. Cross each other. That's something very important. Okay, the lines will never cross each other. And the closer you get, you'll notice that masculine lines will keep start for it. Straight horse start for it. And that means they're becoming more and more uniform, and also they're becoming stronger. So that's when you generate a what pole at the center, a strong magnetic pole. And the further you go, it gets weaker. Do you repel project karo? Can I repel the click to rotate? Yeah, so as they get closer and closer, they will try everything to not intersect, right? And as a result, a gap, right? So that's called the what point? Null point. Okay, so that's the null region where the net magnetic flux or strength is what? 0. That's just what you have. And what is this thing that I'm moving around? A plotting compass. And magnetic field lines represent the direction in which your what points? Plotting compass points. Okay. Right. So let's move on to a new topic. So last class is important. I hope you understand and remember. B is called magnetic field strength or magnetic flux density. It's basically the concentration of field in a place. Phi is how much of the field is there. And A is the area over which it's working. A catch here is that the field must be what to the area? Perpendicular. Okay. And that's how you find it. Now, there's another equation, but there's a term we use very often. It's called magnetic flux linkage. So what's magnetic flux linkage? Magnetic flux linkage, the name kind of gives it away. It's you take one wire like this, right, and it produces its own magnetic field. You take another wire, and it produces its own magnetic field as well. And you keep placing these wires next to each other. What will happen is the magnetic field lines will start to join together, and they'll get linked together, and they'll produce a new magnetic field. There's a net of all magnetic field out there. It's called magnetic flux linkage. And the paper could be easy. You just multiply the phi you have with the number of coils you have. Achha? So I'm going to add Quiraki. I'll just add the formula here. I'm going to topic and a topic, but what's flux linkage? So flux linkage, because I'll be using this word very often. Flux linkage. Flux linkage is BAN. That's it. Okay, and the unit for flux linkage is Weber dash turns. And this N that you see here is number of turns. What does it mean? First of all, what's B into A? Phi, right? So our actor magnetic phi hoy, then if I have like or actor wire phi just phi value hoy. If I have two wires, there'll be how many phi's here? two of them, 3 হলে কি হবে 3 5, so they basically keep what adding up, right? So flux linkage হচ্ছে the magnetic flux that you have into the number of turns you have, and that's why I told you it's a what process, a multiplicative process. I mean, the number of turns 1000 times বাড়াই দেই, what will happen to my flux? Yeah, so it's the easiest way of making a strong magnet. Okay, just increase the number of turns out there. So this is magnetic flux linkage. It হচ্ছে combined field থাকে. Now, why do we mostly use flux linkage rather than flux in our calculation? Because just a single flux, right? It's so negligible, you wouldn't notice anything. So if I have just one individual magnetic field line somewhere, right? It is barely anything. Yeah, what's an example of that? Yes, the Earth. The Earth's magnetic field is extremely weak. It's so weak that your compass barely reacts to it, right? We can't really harness anything out of it. The advantage, though, is that it's very weak and it's very large, and it goes really far out. It goes way beyond in space, which is good for us because it can block what from space? Radiation. Sun's radiation. There's this charged ions out there. They cause solar flares. They kill us, right? But thankfully, the magnetic field just sends them somewhere else. Okay, so let's move on. আমরা এখন হচ্ছে motor effect এ যাব. So page 118. Okay, so just বুঝো এটা. I mean, I think I told you, a topic I'll just go through most stuff. যেগুলো important notes থাকবে আপলোড করে দিব, তোমরা একটু কপি করে নিও। এখন just বুঝার জিনিসগুলো দেখাই তোমাদেরকে। 118. So you have this pole of a magnet, north and south. And can anyone tell me what is the magnetic field pattern going to be in between these two? Quick. Straight. Straight of the middle. My question again, okay? Describe the nature of the magnetic field between two bar poles like this, uniform. And then how do you describe a uniform magnetic field? It's a magnetic field where the field lines are what to each other? Parallel and equidistant, right? So it's just like how your electric field or gravitational field, all fields actually behave the same way. This is easy, and they go from where to where? North to south. Now, what if for simplicity purpose, we assume it's the best magnet out there. So ওগুলো কিন্তু imperfection. Again, in an imperfect magnet, that would happen. We are working with perfect magnets. Now, that's not the point. I mean, don't get excited with this. This is a grade 7th standard question একটা তোমাদেরকে অন্য জিনিস জিজ্ঞেস করতে যাচ্ছিলাম, which is I have a wire here, and you're looking at the cross section of the wire, and the cross here represents the direction of current. What does it mean? Current is going into the page. Okay, so if your current is going into the page and I want to represent that, I'll have to draw a magnetic field around it, which will be a series of concentric circles, right? So like this, like that. Do you agree? Okay, can you tell me what's the direction of the magnetic field? Clockwise or anti-clockwise? Clockwise, right? So if clockwise, I have arrows pointing like this on the top, and arrows pointing like this on the bottom, because you said clockwise. Now that is fine, but there's a thing though. Magnetic field happens to be a vector, and what matters here? Direction, right? So on the top side, you'll find that the field lines are what to each other? Parallel and in the same direction on the top, right? On the bottom, they're what to each other in opposite direction, which would mean that if I see the net magnetic field generated, that the top part will have a what strength? Higher strength, right? So এই জায়গাটা strong হয়ে যাবে অনেক। কেন strong হয়ে যাবে? Because field lines are what here? Adding up, right? And compared to before, নিচে কি হয়ে যাবে? Weaker. Because before there was a field, but it's going to be what compared to before? Weaker. So the upper part becomes stronger. So this becomes more strong, and lower part becomes weaker. And there's this thing in not magnetism, but fielder mode. It's called the catapult effect. So what is the catapult effect? The catapult effect says that when you have an imbalance of magnetic field, strong and weak, right? A force is always exerted from the strong to the weak to return to balance. Why? Because এখানে কি distorted না, and distorted field হচ্ছে sustain হয় না. It's like let's go back to fundamentals. Your diffusion, you have high concentration, low concentration. Why doesn't the particles in the high concentration stay there? Why do they go to the low concentration? Key reason. Yeah, but why is there a concentration gradient? More. Yeah, so can you balance the distribution? Because at the basic concentrate at the calm, right? Energy always tries to flow and disperse. There's this philosophy of energy that it tries to disperse, right? It's called philosophy because it's not proper science yet. Entropic into is not well accepted in science. So, but the idea is that the universe has this, philosophy that it wants to take and disperse energy further and further, and that dispersion is best happen when particles go from high to low and spread it out, right? So তার জন্য এটা হয়. Bottom line here is that from the strong to the weak একটা key generate করা হয়, force, and that force that's exerted on this wire pushes the wire out of this structure, and that force is the first ever evidence of a force generated using a magnet and a current, and this is called the electromagnetic force. Eta হচ্ছে, for us now it is we take it for granted, but when it was first discovered, right, groundbreaking. Why? For the first time you can actually generate force, impact, using current, and then that means you can create devices, motors and everything, and that's why fan and everything else works, right? So like a force generate করা হচ্ছে, and a force কেন হচ্ছে, because there's a strong field at the top, weak field at the bottom. Strong থেকে weak এ wireটা বের হয়ে যেতে যাচ্ছে. কেন বের হয়ে যেতে যাচ্ছে? If the wire moves out of this field, the wire's field would be perfectly normal. The field of the magnet will also be normal, and that's what the universe wants to attain, like a balance, right? So it it becomes balance. So that's where the force comes from. Now, তোমাদের হচ্ছে যেটা জানতে হবে is the name of this effect. What is it called? Yeah, it's called the motor effect. Okay, so example যদি জিজ্ঞেস করে যে this idea that দুইটা magnetic field হচ্ছে interact করে একটা force generate করতেছে, what do you call this effect? This effect is called the motor effect. Do not call this the catapult effect. Catapult effect has nothing to do with motor effect directly. Catapult effect is a reason why strong থেকে weak কি exert করা হয় force. এটা যে কোনো জায়গায় হতে পারে. But the fact that you're using magnetic field of a wire and magnetic field of a magnet to produce force is called what? The motor effect. Okay, and এখানে এই force টা বের হচ্ছে. Now, how do you find the force? I'm still O-level standard again, so I didn't do your A-level stuff yet. How do you find the direction of the force here? Yeah, so we have the Fleming's left-hand rule. So what's the Fleming's left-hand rule? F, B, I, right? F represents force. B is what? Direction of the magnetic field, north to south. I is what? Current. A diagram মধ্যে, where does my magnetic field go from? North to south. So দিকে গেল. Which way is my current? Out of the screen or into the screen? Into the screen. So the first thing, and you should know this by now, don't move your fingers. If you move your fingers, you're doing it wrong. You're supposed to move your wrist. Wrist move করতে হবে, because you have to make sure all the fingers are what to each other at any given time, perpendicular, because you're basically showing that force, flux, current need to be what to each other, 90 degrees, right? By the way, that's a requirement. So our north to south দিকে current is out of the page or into the page. Yeah, so what I'm supposed to do is this: hold this here, and keeping this pointed that way, take this one which way? In, right? So which is my thumb pointed now? Downwards, right? Then that's the force here. That's how you do it, or whichever way you want to do it. Okay, but this is how you're meant to do it, right? That's called the motor effect, and this is called the Fleming's left-hand rule. Clear about that? Now, question হচ্ছে A level say এটা আবার নিয়ে আসা কি দরকার? I think we did enough in O levels. We learned the motor, the working of the motor, splitting commutator, সবই শিখছো তোমরা. So A levels কি? So A levels we'll learn how to find the magnitude of this force, and for that we have our first official A-level magnetism equation বলতে পারো. F equals to BIL sin theta. BIL sin theta. I'm পরে আরো লিখে দিচ্ছি, but what is this F equals to BIL sin theta? So it basically tells you that if you want to find the strength of the force, I mean 3D diagram দেখাতে পারো. Right, so if you want to find the force on this conductor here, আমাদেরকে কি করতে হবে? We need to multiply the magnetic field strength here. Beta বের করতে হবে। এটাকে কি দিয়ে মাল্টিপ্লাই করব? The current in the wire with L. L টা একটু কেয়ারফুল থাকবা। It is not length. It is length, but it is not just length. It is because length মানে কি? আমার ওয়্যার তো এরকম হয়ে অনেক বড় হতে পারে। Do I take the entire length? No, I only take the length that's inside the magnet, right? So the name is called the effective length. Effective length মানে হচ্ছে the amount of wire is inside the magnet. Okay, because your wire could be very long out there, but how much of the wire is only experiencing force, the one that's inside. So এটাকে বলা হয় effective length. Sin theta টা কোথা থেকে আসছে? So sin theta here now tells you that your current can be, or your wire can be at what? At an angle. And still, what can it experience? Force. It's just going to experience what force? Little less. Because key act for a start for it. Components, right? So I'm going to explain for you what I'm trying to show here. So আমার যদি ম্যাগনেটিক ফিল্ড গুলো এরকম থাকে, এটা একটু কেয়ারফুলি দেখো, এটা নিয়ে অনেকের কনফিউশন হয়, they don't know what to break down. So this is my magnetic field, and I have a wire carrying current এভাবে, where the angle it generates, it's theta, and this is the current I, and this is the magnetic field B. আমাকে একটু বলতে পারবা, how do I make the B and I perpendicular to each other? What do I do here? Yeah, resolve into components. Very good. What do I resolve into components? The I or the B? Yes. So the thing is, everyone actually tries to resolve I into the component, and that is not wrong. It won't give you a wrong answer, but current is not a vector. How do you split current up in a component? Do you get my point? Current like a wire ভিতরে যাচ্ছে. It doesn't mean there's like parts of it outside the wire. So যেটা করা উচিত ছিল is এই যে এই বিটাকে you have to break it down. And স্টুডেন্টরা অনেক সময় ভাবে যে এটা দেওয়া, this is much easier, right? Answer চলে আসে, but বিটাকে break down করলে better হয়. How can we break down the B? So মার্স স্কিমের মধ্যে দেখবা যে থেটা দিছে, ওরা থেটা ইউজ করে নাই, ওরা অ্যাকচুয়ালি কি ইউজ করছে? 90 মাইনাস থেটা। সো অনেক সময় স্টুডেন্টদের কনফিউশনটা আসে যে 60 ডিগ্রি দেওয়া আছে, ম্যাথে সব জায়গায় 30 ইউজ করতেছে, বাট অ্যান্সার সেম আসবে। তো কেন? বিকজ আমি যদি এখানে নেই, এটা হচ্ছে cos 60 আর এটা sin 30, they are actually same, right? So eventually কিন্তু ম্যাটার করে না। The point I'm trying to make here, let's get to the important part here, that you can break this B into two components here. একটা হবে এরকম আর একটা হবে এরকম। Do you agree? This is B, by the way. There are two components here. Which component here should I use for my calculation? The green or the blue? মানে এখানে কোন কম্পোনেন্টটা আমি আমার ক্যালকুলেশনের জন্য ইউজ করব? The green one, the one I'm highlighting right now, or the blue one? Yes, because the idea is that your flux and your current need to be what to each other? Perpendicular. এখানে কোনটা হচ্ছে কারেন্টের সাথে perpendicular? The blue or the green? The green, right? এখন I typically show examples like that, and students get used to something. যে সবসময় সাইন ইউজ করে হয়ে যায়, এক্সামে কি করবে? আরেকটা অন্য অ্যাঙ্গেল দিয়ে দিবে, তখন আবার সাইন হবে না, তখন কি হবে? Cos হবে। And you have faced this in projectors. Sometimes they give with the base, sometimes they give with the vertical, right? So the thing that you should remember rather is your current and is your magnetic field what to each other? Perpendicular. ওইটা কেমনে তোমরা আনতে পারো? You know components, right? So that's up to you. But typically হচ্ছে ওরা এই নিচের অ্যাঙ্গেলটা দিলে, what's the quick fix here? Sine. তার জন্য ফর্মুলার মধ্যে কি দেওয়া থাকে? F equals to BIL sin theta. But don't take the sin theta there as a guarantee যে সবসময় sin theta হবে. The sin theta is like a template there to tell you that what plays a role here. Angle. Now এটা sin হতে পারে, cos হতে পারে, depends on what angle you're taking. Also, sin 90 যদি হয়, I will have what value for theta or sin maximum? Sin 91. So that means if sin 90 হয়, it means my flux and my current are what to each other. Yeah, and that's why you have the greatest force when the two things are what to each other? Perpendicular. Or do the angle 0 হয়ে যায়, that means they both are what to each other? Parallel. And it turns out if your field and current are parallel to each other, they will produce no force whatsoever. The field lines don't really interact. Okay, so আমার sin theta ওই symbolic purpose দেওয়া। Do you get my point? That theta can fluctuate for it. I'll just show you one animation, then I'll give you a break, and then we'll do more things next. Right, so this is the motor effect, the one I'm going to show you right now. Motor effect is a force, the electromagnetic force. It has like a very important name in physics. It's called a Lorentz force. A Lorentz force use power you credit the motor effect to Fleming for some reason. Fleming had nothing to do with it. Okay, we credit it to Fleming because Fleming came up with a shortcut to find the answer. What's called the Fleming's left-hand rule. But he didn't come up with the idea that there's a force, or it's somebody else's work. Okay, it's called the Lorentz force. So Lorentz force data. This is the demonstration. So see what's happening here. I'm taking my conductor here. I'll push the conductor into the magnet. You see how the magnetic field is getting distorted. Doesn't it look like one side is getting very compressed, right? So realize on the left hand side, the thing is very tense, like a rubber band pull. So I can do that. I'm holding it right now. It gets thrown out. And that throwing force is the Lorentz force. And that is what we call the what effect, the motor effect. Okay. So it is faster throughout because distortion or beshi. Okay, so that is the motor effect. Now I'm going to do same, it's getting distorted and then thrown out. I think this is easier to understand. Okay. So if you keep altering this force back and forth, and that's use do you know this? You keep altering the magnetic field to make something move. So this is actually advanced maglev trains, magnetic levitating trains out there, or they keep altering the field and that keeps pushing the train forward. It goes like 400 km/h easily. It slopes, and they use this effect there in using very strong magnets, obviously 0.5 Tesla. Okay, yeah, so it's obviously very strong. Anyways, I'll give you 5 minutes break and then we'll start. We'll go through the math here. Okay. He brought everything together. I mean, yeah, we have the Fleming's rules. The glasses. Oh, hey. Ten minutes. The 10 minutes for though. I mean, I'm 5:30. Shawarma. That's a very random request. I don't know any good shawarma place in Uttara. Someone else go. I saw online a review the food poisoning. I don't know. I never ordered from there. Yeah, that's a very big problem. Yeah, I think it is possible. I don't think there's a good burger place in Uttara. I don't like those sauce burgers. Italian? You like sauce burgers? Best burger ever. I had pretty good burgers. The best one. I had this Wagyu burger. Wagyu. A Japanese meat. It's something else. So it depends. I mean, it's obviously more expensive than normal burgers, but it's not that expensive. So Wagyu beef হচ্ছে it's just a type of beef, কিন্তু ওইটার আবার হচ্ছে grade থাকে, ওইটার আবার হচ্ছে হলো কোথা থেকে আসছে, lot of things out there. So ওইটার উপরে prices matter করে. Most expensive Wagyu is like crazy. A5, A5 or B5. Like B5 is like how much fat, or A5 was a marble in their structure. ওগুলা like ওরা slice that's $1,000 for it. Oh yeah, Wagyu যেসব গরুর থেকে আসে, they have like people who massage them every day. তারপর হচ্ছে they have like spa sessions. Yeah, so it turns out that if they have a good life, their fat content বাড়ে. Yeah, they're all stressed. The cows here. কখন লাঠি দিয়ে মার দিবে, when they're getting pampered every day. Turkey has crimes. লাঠি দিয়ে না চায়, no. Yeah, but why should I? It's for children. বাচ্চারা যায়। ওটা তো এখন সব, I don't know, যমুনা ফিউচার পার্কে আছে। The worst thing out there. চম্পার পর লাঠি দিয়ে বাড়ি দিয়ে। I mean, why should I go through like a whole thing to get my ice cream? Doesn't make sense. It's nice to see other people struggle. No, but I felt like I was very close to it. It looks, I don't know, just the vibe of the place is like that. Most tourist places, it feels like someone is looking at your bags. Japan is fucking stuff. Oh no, if you go nearby, একটা জায়গা আছে, ওখান থেকে সবাই তুলবে, ওই জায়গাটা বন্ধ করে দিচ্ছে। But train থেকে তুলে যায়। So the train goes past it. I don't know. No. Oh, yeah. I mean, yes. Iceland was like a thing I thought of. At the moment, no, maybe it's too cold. Whoever went there didn't enjoy it. No, it's good. The castles are good, I admit. But just for castles, I don't think it's worth it. Yeah, I mean, France is okay. It's too touristy. Yeah, it's Spain. No. Yeah. Yeah, I mean the pyramids and heat. That's it. RTS. How long do I stay? There's a rule: 9 days. If you stay in a place less than 9 days, you don't actually get the vibe of it. And if you stay more than 9 days, you start hating it. So it's a big thing. So 9 days before you have to just leave. Yeah, it's okay. Malaysia. Pick the scale and no, Langkawi. Oh, where did you stay? Oh, to live where? In KL? Oh, acha. Yeah, I had plans to go like Johor Bahru. There's a place. Oh, right. I went there for a drive. The casino. Yeah, it's excellent. I mean, the cable car and everything. Really? Oh, a similar thing happened to me in Langkawi. There's a skywalk. You have to go really high. That's super scary. Suddenly you're above the clouds. Agra, Delhi. Yeah, I've been there. Yeah. Yes. So no, South to Jain. I did the Golden Triangle. Agra, Delhi, Jaipur. That's called the Golden Triangle. You're not allowed to go inside. You can see from outside. No. Right. Oh, I had the similar experience. They took me through a separate line, and you have to pay extra for it. So there's an extra fee. You didn't pay that. They'll send you back. Monaco. Monaco is so small. 96 Fahrenheit. Unless you're into gambling, you don't want to live ever. Okay, let's get back. Right. So the formula, and we'll do a couple of calculation here. Oh. Okay, to copy current, the formula is needed. So F equals to BIL sine theta. F is your electromagnetic force. B is magnetic field strength. I is the current. L is the effective length. And theta is the angle between the wire and the magnetic field. Okay. So this is the equation. And তোমাদের আরেকটা জিনিস বের করতে বলে, which I think পারবা তোমরা, but I just want to try it out. Can you find the base unit for Tesla? The base unit for Tesla. Amps. Base unit for Tesla magnetic density. Our polymagnetic field strength, their official definition in your syllabus is actually easy. তোমরা কি করবা, এটাকে সাবজেক্ট বানাবা। সাবজেক্ট বানালে কি আসবে, এটা F divided by IL, right? So magnetic flux density হচ্ছে the amount of force exerted on a wire per unit ampere for per unit length of wire. Basically এটাকে হচ্ছে words এ rearrange করা. But what does it mean actually? It's the concentration of your field. Okay, so yeah, this is the force exerted per unit length carrying a unit amount of current when it's what to the field? Perpendicular. Okay. As equals to BIL center. So is that clear? Confusion the কথা বলতে পারো। No, check it. Yeah, the last one probably not. Also the graphs that you guys asked for. ওগুলা সব explain করেছি।
Recording in progress.
Warmer. I was wondering, I want to কাজ করতেছে না, electricity নাই. That just that তাও চেক করে দেখি, আমি বুঝতে পারতেছি না, is there a light? Sound হলো এখানে? Oh, I don't know, we don't have a generator with this. Yeah, আচ্ছা, এনিওয়েজ একটা এক্সপেরিমেন্ট করবো। বাই দ্য ওয়ে, জাস্ট হেডস আপ বলে রাখি, তোমাদের paper 4 you have multiple experiments. We haven't seen any yet, but they all start from this chapter. So আমাদের এখানে ম্যাগনেটিজমের মধ্যে there are 3 experiments, like they'll just ask you the experiment directly. Okay, so ওরকম এক্সপেরিমেন্টের মধ্যে কি কি আছে বলে রাখি, because some of you have your school exams, so you probably have to need to know. One is to find the force acting on a conductor in a magnetic field, যেটা করবো এখন। আর হচ্ছে there's something called a velocity selector. Do you know what the velocity selector is? Okay. Then there's the demonstration of Lenz's law. You take the magnet in and out and points left, right, and everything. So that, and then there's something called the Millikan's oil drop experiment, where an oil drop paper 4. So paper 4 experiments will keep already jana ase, or just একদম straight OD করতে হবে। Paper 5 এ তো হচ্ছে the experiments are open-ended. They'll just ask you anything random. Okay. Right, so let's see this experiment. It is too interesting at the experiment because it uses Newton's laws and more complicated ideas to get to the answer. So the experimenter naamta ki? Experiment hocche determine the magnitude of F Right, so this is the experiment. To pay attention, so determine the magnitude of F due to motor effect. So what I'm going to do right now is I want to find out the force exerted due to motor effect. The F in F equals to BIL sine theta. But the thing is, I can't use what to find the answer, the equation. So I'm okay, experimentally force the rate. Then I want to compare and see if it matches with the equation. So what I'm trying to do. So we know that F equals to BIL sine theta, right? But let's say we didn't know that formula. How would we find the force? That's what we're trying to do right now. Okay. So this is a magnet provided here. আমরা এই ম্যাগনেটগুলো can use করি কেউ আমাকে বলতে পারবে for experiments এই shape এটা? Why not just 2 bars? Interact. তাহলে তো ভালো, তাহলে we'll have a uniform field. True. Yes, that's one of the points. And the main point is that they're 2 different magnets. So their strength can vary, and therefore you can't have proper uniformity. After strong, after weak, I want to have the same thing. And if they're part of the same setup, right? That's why your horseshoe magnet horseshoe magnet is this one, right? So the strength of the north here and the strength of the south here must be exactly same, because এই dipoles গুলোই তো হচ্ছে realign করে দিকে আসছে। But আমার যদি এটা দুইটা আলাদা বার থাকতো, this could be strong, this could be weak. We wouldn't be able to have this uniformity, right? So you have this magnet here, and then what you do here is place a wire through it to pass current. That's it. So you can wire place for love. My question for you is, how do I find the force exerted on this wire? Brainstorm koro, because তোমাদের paper 5 এ planning question এ এটা random জিনিস আছে. Also, তোমাদের exam গুলোর date হচ্ছে মানে next week, right? 24th, 25th. Mastermind, when is it? Do you know? Physics exam? I don't know. 24 physics হবে 24 আচ্ছা, and তোমাদের? আচ্ছা, so my plan is like magnetism এর মাঝখানে I'll take like couple of days off মানে class হবে, but I'll be just doing question papers. So the question papers এর মধ্যে হচ্ছে I'll do paper 5 as well, because I think paper 5 is going to be there in the exam. Okay, so তখন হচ্ছে ওটার জন্য আমি প্ল্যান করতেছি. So tell me, paper 5 এর question আসছে that you want to find the force exerted on this conductor. How do you do so? How do you find it? আচ্ছা, ওকে ওকে। সো তুমি বলতেছো যে ওয়ারটাকে নিচে রাখবা, তাই না? তারপর ছেড়ে দেওয়া, তারপর এটা উপরে চলে যাবে। Okay, so first thing if you place your wire here, কোনো force হবে না. The wire doesn't move. Cannot. Because all the magnetic field lights at the top, there's no magnetic field in this part. So a horseshoe magnet right, has no magnetic field there. Where's the pin? It's because the dipoles are pointing like that. There's no dipole pointing out here. They're all pointing like that. So mass can be therefore the dipoles here like this, like that, like that, like that, like that. So there's no field there. So Yami, the Lorentz diagram I showed here, আমার তার কিন্তু আটকে আছে কোনো force নাই. Okay, so yeah, ওইটা হবে না. But yeah, if you could তাহলে কাজ করতো. And I don't know if you understood his idea. His idea was to let it go and it'll accelerate, find the acceleration, and then F equals to ma, right? Very easily said, almost impossible to do it in practical. That's because they have to wire move for there's weight acting there, there's friction acting there. There's a lot of things out there. Also, wire to move করতে পারবে না. We don't have enough force out there. So কি করা যেতে পারে? Same. So you're trying to tell me to like make it levitate. As actually could have been possible, but you know what happens every time you have this Lorentz force, right? It always pushes it out. So there's no way that it'll just balance like that. So it'll either fall and then go up, and then fall and then go up, if it was possible, but that requires a lot of strength and doesn't happen. No. Hold the wire. And so there's a force and oh, you're trying to move something with the wire's force. Yeah, so if the thing moves, it means the force is heavier than the weight of that object. Like, how do I find force? Newton meter. Okay, yes, Newton meter. Therefore, what do I do? Ulta hang. Yeah. There's a region there. So do you understand this? I'll keep my Newton meter, and as the wire tries to move, what does it show? A region, right? It won't work. Because your Newton meter has to be inside the magnet. Now you can say, what if we do it that way, right? And the wire tries to go the other way. The force is not enough to actually make changes on a Newton meter. I think the weight will become much higher than that change. I'll cut to the chase. I'll give you the answer. Work like down, right? Right. The energy, the K is converted to the potential. It's called magnetic potential energy, and if you release, it'll jump back up. Oh, the force varies. Okay, so they have come up with an ingenious way of doing this. I was trying to see it's other way to keep it. So the official way goes something like this. It's a lab easy. You place your magnet on an electronic balance first. So you place your magnet on an electronic balance, and the electronic balance will show the what of your magnet, the weight of the magnet. So it's going to show me the weight of the magnet. This much I hope you understand, right? So you have your electronic balance here, and it's right now showing what the weight of the magnet is. And then what you do is you place the wire here, and the wire experiences a force upwards. As the wire experiences a force upwards, can you tell me what happens to the balance reading? It increases, decreases, or remains the same? The wire is moving upwards. What force acting downwards? Downwards. That's okay. So the electronic balance, right? And I'm going to do the same thing right now. I'll turn this on, and this is like, let's say, my magnetic raklam, and the magnet has weight of something. And I take my wire, random wire. Let's say I take wire. and I keep it here, and you're saying that I move the wire like this here, the reading will change. Yeah, nothing will happen. Why do you think that there'll be something that the magnet will experience because you're taking this wire up in the air and moving it around like that? এখানে কি হবে বলো? এটা তো magnet না, it's just a piece of wire. Yes, if I had a magnet here and I brought the magnet close, তাহলে এটাকে ধাক্কা দিবে, reading বাড়বে. If it was the opposite pole of a magnet, কাছে আনলে উপরে উঠার চেষ্টা করবে, reading কমবে. But এই wireটা তো just a wire carrying current, right? কিছুই হবে না. So তাহলে কি করবো? Why did they tell us to use balance here? We don't pass current through it. But reading to change her কথা না. Acha. Okay, I'll explain. I mean, it can because I can directly tell the answer, and sometimes students later on don't really understand কেন এত কিছু করা হচ্ছে. So I'll tell you what you have to do. To make this a successful experiment, the first thing you need to do, একবার তো ওনার Mars scheme শব্দে লেখে, is to use a what wire? A rigid wire, like a rod, not like a very thin wire. Number one. Number two, you take that rigid wire and then you have to what that wire? Clamp it. Clamp it মানে একদম fix করে ফেলবা যাতে the wire can't what anymore? Move. And then you pass what through the wire? Current. As you pass current through this wire, right? This wire tries to move, but it can't anymore because what have you done? You have held it. So because this is not possible for the wire to move here, who rather starts to move because of Newton's third law pair? The magnet. And which way does the magnet move? Downwards. Upwards, not downwards, because তোমার হচ্ছে the wire is trying to go away. Basically, the wire and the magnet are trying to separate away from each other. But একটাকে আটকায় ফেললা, so what will happen to the other one? The other one will start to move. It's basically like this, okay? I'm trying to push the wall with the scale, right? Wall যদি move না করে, কাকে move করাবে? আমাকে. But if I try to move a cardboard here, and it's very easy to move, and I'm the rigid thing now, then the cardboardটা সরে যাবে. So the basic idea here is that if there are two systems out there and you held one stationary, the other one will try to move to create that same effect, right? So যদি clamp করা না থাকতো কি হইতো? If it was not clamp, just jump out like that. But because this can't jump out anymore, right? What happens is that the thing moves downwards and we see a what here? An increase in reading. And the amount by which it increases happens to be exactly what? The amount of force out there. Okay. Now, what if the current was in the other direction? The wire will try to move downwards, but it can't move downwards. So the magnet will try to move which way? Upwards. তখন দেখবে reading কমে যাচ্ছে, which came last year paper. Okay, there were a number that is or also the reading কি হবে. Also, they ask you how to find the force on the reading. Very easy. The reading is in grams. You find the change in grams, convert it into kilograms, and then multiply by 9.81 because weight that বের করতে হবে. So yeah, this is the experiment. বলো তোমাদের questions. Yeah, so the diagram that most students draw is not this version. They draw the top version. So you're just going to draw this, and a wire like that. So draw, you can say that it's clamped at these two places. Okay, but I think this version is more self-explained. Clear about this? Right, so I'll just read through the answer for this. This is the experiment, okay? So, why does the reading on the electronic balance increase when the force on the wire is upwards? And this has a very important keyword in the answer. It's based on what? Newton's third law pair. So let's see what the answer is. As the current passes through the wire, the force exerted on the wire due to the motor effect is upwards. Since the wire is rigid or clamped, it cannot move upwards. The Newton's third law pair of the upward force on the wire is the downward force on the magnet. Equal magnitude, opposite direction, right? So downward force on the magnet. The downward force causes the magnet to push the balance downwards and increases the reading. This increase in mass can be used to determine the force. And that's the force that you see here. And the upper force that you can use F equals to BIL, and you can actually find the what of this magnet. Strength. So how do you find strength of magnet, right? This is one of the ways of doing it, right? A better way, so called the Hall probe. It's this device that does that as well, but this is also one of the ways out there. Also, variations experiment where you need to experiment between current and force. Like if you increase current, what happens to the force? They go to reading the part as you keep increasing the force. So yeah, this is it. This is the end of motor effect, by the way. Motor effect are কিছু নাই. So I'll compile everything and give the notes on it. Our next class যেটা করব, it's called magnetic field and charges. Okay, so it's the next class করব. How much did we finish? 30. না এই জিনিসগুলো ফাস্ট যাবে, বিকজ এগুলো হচ্ছে আগে পড়া, আর এই যে পরে কিছু জিনিস আছে এগুলো টাইম